Ready? Okay, here we go. So singular value decompositions. At the end of this, if I have time, I'll play you a song I found on the internet about singular value decompositions.
Yes.
Yeah, it's like it's based it's based on it had to be you, right? Like it had to be you, right? That's U sigma VT. Anyway, right. So, so how do we? Where were we? Right. We started off with this matrix. And then what we did was we looked at this related symmetric matrix, right? So related symmetric matrix. We, because it's symmetric, you have the Hermitian. You have the spectral theorem, right, which gives you the orthogonal, right, so this is going to be n by n, so n by n matrix, right, orthogonal n by n matrix that diagonalizes, right, so V transpose A transpose AB was diagonal, right? And remember, we wrote that as there's going to be some of the eigenvalues are 0, and some of them are non-zero, right? So this thing here we called sigma 1 squared, right? Sigma 1, remember. Sigma 1, right, the sigmas were, hold on a second. Right, the sigmas, these were actually the square roots of these guys, right? The square roots of the eigenvalues. So this thing is the square. They were R was the rank of A, which was also the rank of ATA. Okay. Right, and then other notation we had was that V1 was the first R columns of V, right? So it was V1 through VR, right? And V2 was the last columns, VR plus 1 through Vn. Okay. And then where we finished was we had obtained, we saw that A could be written as A V1 V1T, and then we did something peculiar, which was we let U1 be A V1 sigma 1 inverse, and then we have an expression A equals U1 sigma 1 V1T, right? Which is a little bit phony, right? We basically forced it to have the kind of form that we wanted. Okay. Right. So this thing was the compact singular value decomposition. Okay. And what was wrong with it? What we want. We want A to be expressed as U sigma V transpose, where each of these guys is each of these guys, that was M, this is M, right? Where the guys on the outside are square orthogonal matrices, and this guy in the middle is an M by N with the singular values down the diagonal. So we're gonna get to that thing from this thing. Okay. Okay. So it's a little bit strange, but let's think about this thing here. So V1 transpose is pretty good, right? V1 transpose has some nice qualities, right? These things are an orthonormal basis, right? So notice that the columns of V1 are orthonormal. Okay. Why is that good? Because we're hoping, right? We're hoping to have an orthonormal a matrix that's orthogonal, right? That's where all the columns are orthonormal. Okay. We just need to sort of like build it up, right? We have you know, we don't have a square matrix here. But what about this one? What can we say about this one? Are the columns orthonormal? So here's the question, right? What's good about this? What's good about U? U1. What's good about U1? Right? You'd like it to be, you'd like it to have some of the characteristics that we want of U, right? And indeed, it turns out that that it does. So, I guess my point is that this U was kind of contrived, right? We sort of pulled it out of we created it in order to make this expression. Is it really a good thing? It actually is a good thing. Okay, that's the point here. Okay, so let me put on my glasses. Okay, so let's examine U1. Okay, so U1 is this A V1 sigma 1 inverse. Okay, so let's write it out. It's going to be AV1, right? Remember, V1 is this guy here. So you hit it on the left side with a matrix. It acts row matrix-wise, column-wise. So you get AV1 and AVR, right? That's this thing, right? And then we also have this square root of sigma 1. I'm sorry, this inverse of sigma 1. Well, the inverse of sigma 1 is going to be 1 over the square root of square root of lambda 1, 1 over the square root of lambda 2, 1 over the square root of lambda r. 1 over the square root of lambda r. Right, that's the inverse, right? We multiply sigma 1 by it, we get the identity. Right. That's clearly the inverse of sigma 1. Okay. Okay, so now we multiply those guys together. What do we get? We get, when we multiply this diagonal matrix by this thing, well, each of these things is going to multiply the corresponding column, excuse me, right? And so we end up with AV1 over root lambda 1, AV2 over root lambda 2, and so on and so forth. AVR over root lambda r. Right? That's what U is, right? And let's give those guys names, U1, U2, UR. So let's notate those columns of U in our usual way with the lowercase letter. Okay. So now, right, we would like this thing to be an orthonormal, we would like these guys to be orthonormal, right? That'd be great. In fact, they are. So let's see that. So now observe. If we consider, ui transpose times uj, so we get the dot product. Well, ui transpose is going to be, right, so ui is of course 1 over square root of lambda I avi, right? So when we transpose it, we're going to get, that constant just comes out. We get vi transpose a transpose, right? That's this thing, right? And then we also get this 1 over root lambda j avj. Everybody okay? Okay with that? Any questions? Right. This is ui transpose. This is uj. Okay. Let's pull the constants out. We get 1 over root lambda I lambda j. Then we have this vi transpose ata vj. Okay. Can anybody remember what the v's were? Where did the v's come from?
Like V1.
They came from v1. Where did v1 come from?
It diagonalizes ATA.
Exactly. Diagonalize ATA. In other words, it is, if it diagonalizes ATA, these guys are
Orthonormal.
not just, they were orthonormal, but better than that. Because they diagonalize it, they are the
The eigenvector?
eigenvectors. Great.
Yeah.
They are the eigenvectors of ATA. Exactly.
Right.
Yeah. +2 for you, Kate. Yeah, they're the eigenvectors, right? So when we hit this thing with ATA, well, it just turns into lambda j vj, right? Right. So that lambda j, well, a square root of it cancels out, and we end up with, so this thing is this thing. So we end up with lambda j, root lambda j on the top, root lambda I on the bottom, vi transpose vj. Right. So I'm just pulling the factor out. Okay. What's that? By what Izzy said, this is 0, or it could be 1 if I is equal to j.
Yeah.
Right. So this is going to be 0 if I is not equal to j. This is going to be 1 if I equals j, and also you notice that the factors will be 1, right? Because you have root lambda I over root lambda I. They'll be the same, right? So it's 1 if I equals j. Oops, 1 if I equals j. In other words, these guys are orthonormal. Okay, so columns of U1 are orthonormal. Okay. For those of you going to mathematics, I don't think I introduced this notation, but this notation basically means 0 if I is not equal to j, and 1 if I equals j. Okay, it's called the Kronecker delta notation. and one sees this all over the place. So this just means we could write this as parameter ij. You've seen it in physics. Okay. Okay. Okay, so that's good, right? So, right. So that U1 that we made up to make things look like a singular value decomposition actually was, had orthonormal columns. Okay, so now we do something a little peculiar. So we so observe that the U1 to UR, as we just said, are orthonormal and lie in the range of A to A, which is the same thing as the range of A that we saw earlier. And the dimension of the range of A was R. So since the dimension of the range of A was R, right? The rank of A was R. The U1 to UR are an orthonormal basis for the range of A. Okay. So, so we extend. So this is something I didn't talk about. I don't think I talked about. Were in any of the lectures online? Did I talk about the Gram-Schmidt process? Doesn't look like it. Okay, so if we have time, I'll do that. I'll do that later. But so there's something called the Gram-Schmidt process. So it's possible to extend an orthonormal basis of a subspace of Rn to an orthonormal basis of all of Rn. Okay. Roughly speaking, what happens is, you have some subspace, of Rn, and right. And maybe you have an orthonormal basis for it already, right? You have an orthonormal basis for that part, and you'd like to get an orthonormal basis for the whole space. And what you do is basically you just choose some vector that you choose some vector independent of the other vectors, and then you throw off the part that's not perpendicular, right? You decompose this into the perpendicular part and the non-perpendicular part, and you keep the perpendicular part, and then you rescale it. You rescale it to size 1, and then it becomes an orthonormal. Then you've got an orthonormal. You've got one more step towards your orthonormal basis, and you just keep on going. Okay, so that's. I hope at least that's intuitively believable. Okay. So what you do is you, say, using Gram-Schmidt, one chooses an orthonormal basis of RA perp right? We have an orthonormal basis for Ra. We choose, we choose an orthonormal basis u r plus 1 to r un of Ra perp, sorry, m of Ra perp, which is, remember, the null space of 18. Okay, and then let u be just those two things together. So u1 the ur and ur plus 1 the um. So we just complete the complete the orthonormal basis, and we make a matrix out of that orthonormal basis. Okay, this part over here was u1. Let's call this part u2. Okay, then this u, which is an m by n matrix, is orthogonal. Okay. Right. Remember what we're trying to do. We've got the compact singular value decomposition. We're trying to make the full-blown singular value decomposition, right? So we've got sort of like part of the matrix on the left-hand side. We've got part of the matrix on the right-hand side. Now we've got the full-blown matrix on the left-hand side. Okay. Now we've got the actual U on the left. We sort of built U out of U1. Okay. Okay. Does that make sense? At least story-wise, where we are in the story. By the way, my daughter has apparently decided what college she wants to go to, but she hasn't told me. She won't tell us. Yeah. The due date, the deadline is tomorrow. Yeah, the deadline is tomorrow. So she's like, I think I've decided where I want to go, and the whole family was like, and then she said nothing. Staring at her, and she says, yeah. Okay. Okay. So, okay, and that's actually enough to do it. So now that's it. Now consider. Let's look at U sigma VT. Let's look at U sigma VT. Well, that is this U1, U2. That's U1, U2. And then remember what sigma was. Sigma was, sigma 1 is up here, and then a bunch of zeros down here. Right? And then, remember what V was, right? V was V1, V2. V transpose is going to be V1 transpose, V2 transpose. Okay. Okay. When you multiply these things out, what you get is what you get is sigma 1 V1 transpose up here, and then 0 down here, and this just stay still for now. Right. And then when you multiply these matrices out, you get U1 sigma 1 V1 transpose plus 0. But U1 sigma V1 transpose is a complex singular value decomposition. So that's it. Okay. In some sense, all the work was done here, right? All the work was done here. This stuff is just, this U2 has no effect at all, right? This U2 has no effect at all because, right, when you multiply it out, you get U2 times 0, right? So we could have put anything in for U2, and it still would have worked out to be this. The only thing is that if we stuck in anything here, then we wouldn't have an orthogonal matrix here. We do want an orthogonal matrix there for reasons that will become clear later. But in terms of just getting to A, U2 could be anything. And V2 could also be anything. Okay. So let me sort of sketch out the procedure again of how you get it. How does one get a singular value decomposition? There's basically a procedure. One, you find the orthogonal such that that diagonalizes ATA, right? So A is an n by n. So find this guy that diagonalizes ATA. At the same time, determine the decreasing eigenvalues, lambda 1 through lambda r. Right, where these last guys are all 0, say, and create sigma from them. Right, so sigma is that thing. It's an n by n matrix, but it's got these guys down the upper diagonal. Okay, then 2. The first r rows of U are constructed as as 1 over lambda I, 1 over the square root of lambda I, ABI, and the rest are constructed via Gram-Schmidt. Okay, so these guys here are an orthonormal basis of the range of A. These guys here are an orthonormal basis of the null space of A transpose. I mean, I should just write this RA per. Okay. And then that's it. Then you've got the three pieces, right? So you have U, you have sigma, and you have V, and that's your singular value decomposition. Then A equals U sigma VT is the singular value decomposition. Okay, let me give one kind of simple example of how this could be done. I'm just going to follow the procedure. Okay. So a kind of simple example. I'm going to do one which doesn't require doing the Gram-Schmidt process, since we haven't introduced it yet. So you have a matrix. A is 2, -2, 1, 2. Okay. Then you calculate ATA is, you do it, of course, and it turns out to be 5, -2, -2, 8. Okay, so, right, we want to diagonalize this, right? We want to find an orthogonal matrix that diagonalizes this. So, to constructing V, we need to, one, calculate eigenvalues. And what you see is that there are 2, 9, and 4. Okay, and then you can get eigenvectors. 1, -2, and 2, 1. So this one is from eigenvalue 9. This one is from eigenvalue 4. Okay, and then they're perpendicular to each other, and you just need to normalize them. So divide each by its magnitude, square root of 5, right? And that gives us so we get our orthonormal basis. Okay, so that gives us our V. Our V is going to look like 1 over root 5, 1, -2, 2, 1. Okay, so that's our V, and then we just need to get the U, and we get the U, like this. Right? The U's are obtained from the V's, right? So U1 is going to be, 1 over the square root of the eigenvalue, right? Times AV1, right? So A and then V1. Oops. Right, U2 is going to be 1 over the square root of the eigenvalue, A V2. Which works out to be which this one works out to be 1 over root 5 to negative 1. And then this one works out to be 1 over root 5. So u looks like 1 over root 5, 2, negative 1, 1, 2. Yeah. Okay. So then in the end you get that. So our singular value decomposition is that our matrix 2, negative 2, 1, 2 can be written as u 2, 1, negative 1, 2. Then 3, 0, 0, 2, and then 1 over root 5, 1, 2, negative 2, 1 transpose. B is that. Okay. Yeah.
A specific question.
Yep.
If you have like a 2 by 2 matrix
Mhm.
and you do get one of them is a 0 eigenvalue,
Yeah.
could you just solve for its like one eigenvector to get the second like the extension rather than doing the Gram-Schmidt if it's only a 2 by 2?
Could say that last part
Like, so
again?
if you get, like, I don't know, 9 and 0 or something,
Mhm.
if you solve 9 for its normal eigenvalue,
Yeah.
could you also solve 0 for its eigenvalue, because there's only gonna be one of them to make it a 2 by 2? Could you then just be like, that's also gonna be perpendicular and that's gonna work and make it a orthonormal basis?
So it has 2 eigenvalues.
Yeah, one of them is
One of them-
non-zero and one is 0.
One of them is 0.
But because only one of them is 0, its one eigenvalue is gonna be the extension essentially.
Yeah. Yes, I think so.
Okay,
Yes.
perfect.
Okay. Okay. Are people okay with the process? Right. So. Okay. So. Yeah. So, like I said at the beginning, this is sort of like a diagonalization, a way of diagonalizing things. It also has a much more important function or role, which I'll try to explain. Maybe not right now, but yeah. So you're probably wondering like what's the point of the singular value decomposition? Like we did all this work, we showed that we could do it. Now we did it. So what, right? So what? The real use of it is in creating approximations of your original matrix. Okay, and basically what happens is that for example, in this case, if we look at suppose we take our singular value decomposition and then we just use only one of the eigenvalues here. Okay, we use only one of the eigenvalues here. That will give us a matrix. What's the relation between that new matrix and the old matrix? Okay, it turns out that this new matrix is in some sense the best approximation, the best rank 1 approximation of the old matrix. Okay, so in general, what you're going to have is something like something like this. Right, you have the square roots of the eigenvalues down like this, right? 0 here, the transpose, right? And you know, this could be some sort of gigantic matrix, and so you know, this singular value decomposition, you know, represents the whole matrix, but you can like chop it down to like maybe like 10. You take only the first 10 eigenvalues here, and then that would give you a rank 10 approximation of your original matrix. Okay, rank 10 approximation is very good, right? Because that means that you can express this approximation as a linear combination of just 10 vectors, right? So you can compress the data, right? You can compress the data. This is a, you know, like in terms of image compression, this is one way of doing an image compression. I think they have pictures in the book of various examples of that, right? Like, you know, they have the original picture and they say, okay, now here's the, you know, rank 10 approximation, right? And you think the amount of, you know, you need to store the information for those 10 vectors, and then you need to store the information for what the coefficients are for the linear combination. That's it, right? That's it. And then that's much more efficient than storing every single bit of information over here. Okay. So yeah, so the real point of this is that one can, so what's the point? One can easily construct rank k, where k is smaller than r, approximations from the SVD. Okay, and in fact they are the best, or yeah, in some sense they're the best. Okay, and yeah, this is what I think, Ella, you were talking about, right? That you basically that you can. It's sort of like the least mean squares thing. I should give you at least 2 points for that. Yeah, why not?
I appreciate it.
Okay, 5 minutes left. So we'll do that next time. But let me just make some comments. Okay. Okay. So just some additional terminology. Definition. We call the Vj the right singular vectors. Okay. We call the Uj the left singular vectors. Okay. So, remark, this we kind of said already, the Vj are the eigenvectors of ATA, where the first R of them are an orthonormal basis of the range of A, the range of A to A, which is the range of A transpose. Is that right? Yeah, the range of A transpose. Sorry. And then the last n minus r are an orthonormal basis of the null space of ATA, which is the null space of A, which is the range of A transpose per. Two, this is kind of a funny thing. So remember A is U sigma V transpose. What if we look at AAT? AA transpose is going to be U sigma V transpose, and then this thing transpose, which is V sigma transpose U transpose. Right? What's V transpose V? What? Right, the identity, right? Because this is orthogonal, right? So that just vanishes. So this turns into U sigma transpose UT. But sigma transpose is diagonal, right? This thing is diagonal. Right? It's a diagonal square matrix. Right? So the observation is that, right, what's the point? Just as V diagonalized A, I'm sorry, ATA, U diagonalizes AAT, right? Right? You see that U transpose A T transpose U is diagonal. Right? And so there's a symmetry. The first R are an orthonormal basis of the range of AAT, which is the range of A, and the last are an orthonormal basis of the null space of AAT, which is the range of A perp. Okay, so there's sort of like a symmetry that happens. It's not so important, I think. But it's true. Okay. Let me just say one last thing. So there's some relations between the right and left singular vectors. Right. AV equals U sigma tells us that AVJ equals sigma j Vj. Remember, sigma j was the square root of lambda j. Okay, so the matrix maps. We kind of knew this, right? Actually, we knew this already. Right? This is how we made the U's. This is how we made the U's, but it's true for all of them. Okay, and then similarly, ATU equals V sigma transpose tells us that A transpose Uj equals sigma j Vj. Okay, for j equals 1 through n, and equals 0 for j bigger than that. Okay. saying, right? I just put these up, but they're not going to play too much of a role in what we're talking about. Okay, so just some relations between the right, some comments about the right and left singular vectors. But next time, what we'll do is we'll talk about why how we can get the low rank approximations from the singular value decomposition. And that will be the end of that. Okay, let me give back the exams that you kindly brought the other day.